G'day viewers. In this episode we're going to do something a little different. We're going to address the difference between a scientific law and a scientific theory. To many viewers, the difference between a scientific law and a scientific theory is obvious, understood and well known. If you're one of those viewers, then I apologise in advance for dragging you through this. However, it has been my observational experience that a cohort of viewers exist who do not know the difference between a scientific law and a scientific theory. For example, some people do not seem to comprehend that physical laws cannot be broken, bent or spindled. They are rigid and apply universally throughout the cosmos. They work everywhere in the same way that they work on Earth. A couple of examples of physical laws are the conservation of energy and the conservation of momentum. This means that these laws cannot be broken in any way, shape or form and must be obeyed all the time, without exception. In fact, Wolfgang Pauli believed in the laws of conservation of energy and momentum so strongly that he predicted the existence of the neutrino in 1930. So what about a scientific theory? How is that different to a scientific law? Well, you can find various descriptions on the internet, but my personal favourite is this. A law describes natural phenomena, but a theory explains why those phenomena occur and/or how those phenomena might be linked together. In other words, scientific theories are more overarching explanations of how nature works and why it exhibits certain characteristics. Thus, it should be easy to see how scientific laws differ from scientific theories. Okay, so what is an example of a scientific theory? Well, possibly the most famous example in popular culture is Albert Einstein's theory of general relativity. It is critically important to understand that general relativity is a scientific theory by community-wide acceptance. It is not considered to be a scientific law of any kind. Unfortunately, there seems to be a cohort of people in viewerland who mistakenly believe that general relativity is so well tested and verified that it takes the status of a scientific law rather than a scientific theory. However, this is not the case at all. General relativity is a theory, not a law, and this isn't just my opinion, it is widely recognised and accepted fact by the scientific community. So far we have discussed the difference between a scientific law and a scientific theory. So then, what happens when the two of these collide? Well, when this happens, the scientific theory needs to be revised, completed or adjusted. In the case of an expanding universe, astrophysicist Ethan Siegel argued in a Big Think article published on the 2nd of May 2023, which we discussed in episode 81, that the law of conservation of energy does not apply to the context of an expanding universe. In other words, an expanding universe violates the law of conservation of energy. The problem we now have is we know for a fact that the universe is not only expanding, but expanding at an accelerated rate. So what does this mean for the theory of general relativity? At this juncture, I urge viewers to watch episode 81, but the bottom line is that the theory of general relativity is either broken, or more likely and realistically, it is an incomplete theory. In fact, it is widely accepted by the quantum physics community that general relativity is somehow incomplete because it does not integrate with quantum mechanics in any well-accepted manner. This isn't my opinion, it's the opinion of most professional physicists globally. However, for some bizarre reason, there seems to be a cohort of viewers out there who simply cannot accept Albert Einstein as anything other than a cult figure genius. Let's put Einstein into perspective, shall we? Let's compare him to Pythagoras, Da Vinci, Fourier, Newton or Maxwell. When we compare Einstein to any one of these other names, we can clearly see that by comparison, Einstein was not a genius. His impact upon the way we live, the way we experience the universe and the manner in which we study it is trivial compared to Newton or Maxwell. Imagine the state of civilization without Pythagoras, or without trigonometry, or without algebra. Imagine trying to study the cosmos without the instrumentation possible via Maxwell's equations. So the cult of Einstein is very clearly undeserved. How the cult of Einstein has managed to manifest itself is a mystery to me. How one person can be pushed to the front of public consciousness so forcefully is bizarre in my view. Perhaps it is somehow connected to narrative control via the mass media. Perhaps it is somehow connected to religious faith. Who can say? At any rate, it appears that there are a cohort of viewers watching who seem to believe that Einstein was the greatest mind to have ever lived. Well, this simply is not true. Einstein is just one voice in a chorus. Okay, let's now summarise our overall position. Basically, general relativity violates the law of conservation of energy with respect to an expanding universe, and therefore is fundamentally flawed. General relativity requires fixing, and the form of this fix probably involves quantum mechanics. We discussed in episode 81 how we believe the fix involves the quantum vacuum and quantum electrodynamics. We explained that by switching on general relativity, one switches off quantum mechanics. By switching off quantum mechanics, general relativity violates the law of conservation of energy because it automatically ignores the fundamental building blocks of nature. General relativity does not address the fundamental structure of nature in any manner, not in any way at all. And this is a major problem in terms of a grand unified theory, that is, in terms of a theory of everything. As we mentioned in episode 81, general relativity applies exclusively to a bare vacuum, not a quantum vacuum. A bare vacuum has no quantum properties whatsoever, none, not a single one. The problem with this is that it simply isn't reality. It's complete fantasy, a total fiction. We physically live in a quantum vacuum. This is experimentally proven fact. We do not live in a bare vacuum. We do not live in the kind of space-time manifold envisioned by Einstein. This means that general relativity completely ignores the experimentally confirmed Casimir effect and therefore completely ignores the virtual particle pair creation annihilation process associated with the Casimir effect. If this isn't obvious to you, then my suggestion is for you to do more reading. We know that 67 to 68% of cosmological mass exists in the form of dark energy. However, nowadays, physicists artificially try to rescue general relativity by imbuing its cosmological constant with properties of dark energy, but that's a rescue operation. Dark energy was not explicitly stated to exist, nor predicted to exist by Einstein. Modern-day cosmologists are being too generous to general relativity by explaining away the cosmological constant as being a manifestation of dark energy. There is no evidence confirming that Einstein's cosmological constant is truly constant, or that Einstein meant it to be interpreted as dark energy. In fact, Einstein himself regarded his cosmological constant as being his greatest blunder. So it is a matter of verifiable historical fact that Einstein was just guessing about the function of his so-called cosmological constant. Coming back to the distinction between scientific laws and scientific theories, we can state with certainty that, in the case of an expanding universe, general relativity fails spectacularly because it violates the law of conservation of energy. Remember, we're talking about violating a physical law, not a guideline or local government regulation. There is no way to sugarcoat this, or somehow interpret that general relativity remains some sort of acceptable exception. General relativity violates the law of conservation of energy and therefore is fundamentally flawed, or at the very least, general relativity is an incomplete gravitational model. So then, why do a cohort of viewers, some with a good working knowledge of general relativity, still insist that ignoring the violation of the law of conservation of energy is an okay thing to do? Well, it's difficult to answer on behalf of everyone, but my best guess is that most people who understand general relativity well do not understand quantum electrodynamics or the principle of the quantum harmonic oscillator. If they did, I believe they would also come to recognise that general relativity has some issues and the law of conservation of energy is a critical one. Therefore, my advice to everyone is to study general relativity, but also study quantum mechanics, the quantum vacuum, quantum electrodynamics, and the quantum harmonic oscillator. An expanding universe, as understood by general relativity, violates the law of conservation of energy. Quite simply and frankly, this is an unacceptable outcome. Clearly, general relativity is fundamentally flawed, as echoed by the quantum physics community. Anyway, that's enough from me. Thanks for listening, and I'll see you next time.